Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because, hey, this hour is your hour. Okay, well, without further ado, let's jump right into some of the listener phone calls.
Hello, Professor. My name's Jared. I'm calling from Winnipeg. So here's my question. I know that you cannot have faster than light communication, but say that you could by using quantum entanglement. What would happen if you had two devices connected by quantum entanglement and we kept the receiver and then we sent the transmitter into a black hole? Because the closer to a singularity you get, the slower time goes. And I've heard that from the inside of the event horizon, looking out, the universe appears to be going in fast motion. So would you care to speculate as to what that could mean? Could we possibly have a sneak peek into the future of our universe using a device like this?
Well, you're asking a whopper of a question, I must admit. So let's try to break it down piece by piece, and we'll find out that your question is not as outlandish as it sounds at first. First of all, what is quantum entanglement? Quantum theory is basically atomic physics. It's the theory of the atom, where lots of really weird things happen at the atomic level. Now, we're large objects. We consist of trillions upon trillions of atoms, so we don't see these quantum effects. They all average out for big things like us. But at the atomic level, you see all sorts of bizarre things happening. Electrons can be two places at the same time, for example, disappear, reappear someplace else. These objects make possible lasers. They make possible transistors. That's why the world of electronics seems so weird and bizarre. By rights, transistors and lasers shouldn't exist. So let's break it down. Quantum entanglement. Electrons are particles that have spin. They spin like a top. They can spin up or they can spin down. Let's put two of them together and then separate them. So it means that if you start with a state of zero spin and you separate them, one electron has spin up and the other electron has spin down, such that the sum of the two is zero, because together they have no spin at all. However, quantum mechanics says that as you separate these two electrons, an umbilical cord, an invisible umbilical cord emerges connecting the two, so that if you know that one is spin up, the other is spin down. Now, how fast did you figure that out? Well, instantly. As soon as you know that the first electron is spin up, you know instantly that the second electron is spin down. At this point, Einstein comes in and says, no, nothing can go faster than light. Therefore, it is impossible that information can travel from one electron to the other electron. Ha! Well, Einstein thought he finally killed quantum mechanics with this quantum entanglement. However, since then we've done the experiment. Einstein was wrong. I mean, what can I say? It turns out that, yes, some kind of information does instantly go from one electron to the other, and that's called quantum entanglement. Now, to be fair, Einstein has the last laugh, because you cannot send usable information faster than the speed of light. And so, did something go faster than the speed of light? Yes. Information went faster than the speed of light. If one electron is spin up, now the other electron, perhaps now on the other side of the galaxy, is spin down. However, you cannot send Morse code this way. You cannot send a telephone message this way. You cannot send usable information. All you can send is random information, which is largely useless. And so for those people who watch Star Trek, on Star Trek they have subspace communicators, where Captain Kirk can instantly communicate halfway across the universe with Federation headquarters. Well, even quantum entanglement will not make that happen. Now, the listener asked a second part to the question. Let's say I have two electrons that are entangled, and I put one into a black hole. time beats at a different rate near a black hole. In fact, time seems to slow down as you get closer and closer to the black hole. Therefore, you now have a telephone line connecting two objects beating at different velocities. In other words, beating at different times. And so can you use that to talk to the future? That's the question that was being asked. Well, the short answer is we're not sure. There have been a rash of papers written just in the last few years trying to make a link between wormholes and quantum entangled electrons. A wormhole is a gateway through space and time. We think that a wormhole exists at the center of a black hole, and so a black hole in some sense is a gateway to a parallel universe. So, says the listener, let's now put one electron through the black hole, through the wormhole, and winds up on the other end of the universe. Can it communicate with the first electron, which is sitting normally, let's say, near the planet Earth? Can you therefore communicate with somebody in the future, communicate with somebody on the other side of the galaxy? Well, at first I would say no, because only random information can go faster than the speed of light. And random information, as you know, is rather useless. You can't send messages. You can't make a telephone call faster than the speed of light. But hey, we don't know because we never found the wormhole before. We don't know its properties. They are solutions of Einstein's equations, but we don't know how stable they are. So it's a big question mark. So the simple answer to your question is we don't know. The bottleneck is the wormhole. We have yet to see a wormhole. They are predicted by Einstein's theory, but how stable are they? Most calculations show that wormholes are not stable. If you watch Star Trek, of course, they use wormholes to go across the galaxy. Well, maybe, maybe not. But we need a more advanced theory than Einstein's theory to resolve the question of the stability of the wormhole. Will the wormhole close as soon as you go inside and cut you in half? That would be a disaster. That would be a rather useless wormhole. We don't know. It requires a higher theory called string theory. String theory, however, is so mathematically complicated that we have yet to find a solution of a wormhole that is stable. Now, ultimately, I think string theory will resolve the question. But right now, to be very frank, we're not smart enough to solve the equations. And if you want to see what these equations look like, if you think you're smart, get a copy of my book for PhD physicists called Introduction to Superstrings, and you can see some of the equations that would be required to solve the question, can you talk to the future using a telephone system of two electrons connected by a quantum umbilical cord? Okay, wow, what a question. Well, let's move right along and take the next listener phone call.
Hello, my name is William Lee. I've been a huge fan of your show Sci-Fi Science and Exploration. I was just wondering, what are the odds of genetic engineering one day giving us, like powers or something like electricity, from X-Men and stuff like that? Thank you.
Well, I think every kid reading comic books like the X-Men say to themselves, wow, I wish I could do that. I wish I could fire bolts of electricity, bolts of flame from my hand. But then when you go to school, you learn there's something called science. And you learn that there are rules governing things like bolts of lightning and bolts of flame. And you begin to wonder, well, is it really possible to create some of the things that you see in the movies and in the comic books? Well, the answer is yes and no. For the most part, you can't. For example, Superman is invulnerable. Nothing known to science can dent the skin of a Superman from Krypton except kryptonite. And, of course, since they never explained the radiation of kryptonite, we scientists do not know whether kryptonite can even exist at all. And so when it comes to a Superman of superhuman powers, we tend to think that, nah, that's probably not possible. Now, Spider-Man, on the other hand, well, there is a rhyme or reason to that. For example, scientists have very carefully studied the silk of spiders. It turns out that ounce for ounce, you can show that the silk of spiders is as strong as steel in some areas. And if you could process it correctly, then perhaps you could create a spider webbing of some sort. And so that's within the realm of possibility. What about invisibility, like Invisible Girl of Fantastic Four? She can zip around and she can become invisible. Well, believe it or not, the United States Pentagon has invested millions of dollars perfecting the stealth bomber, which is not really invisible, but invisible to radar, but visible optical invisibility that's also being looked at. It turns out that using something called nanotechnology and metamaterials, it is possible in principle to create something that is invisible. In practice, the only object that we've made invisible is basically microscopic in size, but it's an engineering problem to scale it up. So invisibility is possible, but it's an engineering feat that we have not yet perfected in the laboratory. Well, let's take a short commercial break. And after the break, we'll say a few things more about superheroes and the comic books, and we'll take your listener phone calls.
This is Science Fantastic. You're listening.
Kaku, the lines are open. Well, before the break, we had a call that I sometimes get from kids who are fans of the comic books, and who isn't. And that is, well, the superheroes you see out there, is it really possible that one day we can harness their power? Well, let's break it down one by one. What about shooting bolts of lightning or flames from your hand? Well, electricity has its own laws. If you take a course on electricity, you know that electrons like to go to ground. There's a potential, that is, you are, let's say, 1,000 volts above ground, and therefore electrons want to go to ground. They go to the place of lowest potential. And so can you shoot bolts of lightning from your hand? And the answer is only if the object you're pointing at is at ground. And so in other words, by simply waving your hands and forcing electricity to go zapping from your fingertips, it doesn't work that way. Electricity has its own laws, and the electrons will go to ground. That is, they'll go to the floor, it'll go to a faraway pipe, it'll go to some place where the electrons are at zero voltage. And so you're not going to be able to throw flames of lightning bolts like Electro, one of the enemies of Spider-Man. Well, what about the Human Torch? Well, first of all, the Human Torch can fly because flames are lighter than air, as they say. But you have conservation of mass, and therefore you simply cannot take a human being, convert them to flames, and have them float. But what about the flames themselves? Is that possible? Well, it turns out that if you have high temperatures, they tend to go through materials very rapidly unless you have an insulator. Now, one day, perhaps nanotechnology may give us a nano insulator that would be paper thin, that would separate you from a flame. But right now, we don't have that. We don't have any such nano insulators that can do that. One reason, for example, why you put on layers of clothing when it gets very cold outside at wintertime is because air is an insulator, believe it or not. And that's why your mom was right. Wear layers, because air, which we don't think of as an insulator, is a very good insulator. Well, we want an insulator even better than that, so you don't get singed if you have a flame outside your skin and you somehow can throw these balls of flame. So the Human Torch, well, we may have to wait until we perfect something called nanotechnology. Well, what about telepathy? Telekinesis. After all, the most powerful of all X-Men is actually a woman, and that's Phoenix. Phoenix has the power to destroy planets, for God's sake, and stars. She is by far the most energetic, most powerful superhero in the comic books, except for Superman. Unfortunately, the Phoenix died. But nonetheless, is it possible to create somebody of that kind of power? Well, we'll answer that question after the break. Telepathy, telekinesis, the power of Charles Xavier, the power of Phoenix.
Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, well, before the break, we had a call about superheroes. Are any of the superheroes possible? Well, yes and no. We said that some superheroes are highly unlikely, like Electro, that can shoot out electric bolts from his hand. But what about telepathy and telekinesis? Normally, scientists would have said, ha, preposterous. There's no way that we can have telepathy and telekinesis. That's for circus shows, basically. That's for the naive and the gullible. Well, not anymore. We can now do that in the laboratory. Get a copy of my book, The Future of the Mind, and you realize that we can now connect the human brain to a computer, and via the computer we can now communicate with people that are paralyzed. People that can't even scratch their nose because they are paralyzed. We can now communicate with them, and we can now give them the gift of mobility by connecting their brain directly to an exoskeleton, a mechanical skeleton that allows them to walk and allows them to have a semi-normal life once again. Find out how it's done by getting a copy of my latest book, The Future of the Mind. And if you connect the mind to a power source, the power source in turn can then move machines, and then you will have the power of telekinesis. That is the power of mind over matter, the ability to move objects with your mind. I remember one episode of Star Trek when the crew of the Enterprise lands on a planet with Greek gods. They meet Apollo, the sun god of the ancient Greeks, and he has this enormous power that only gods can have. And Captain Kirk says to himself, hey, wait a minute, something is fishy. There's no such thing as Greek gods anymore. So how can we have Apollo here doing all these fantastic feats of magic? He says to himself, I got it. There must be a hidden power source. All he does is telepathically make contact with the power source, and the power source does all the magic tricks, making it seem as if he is a Greek god. And so they locate the power source, they zap the photon torpedoes at the power source, and boom, Apollo becomes a mortal man. And that's how telepathy and that's how telekinesis is possible once you have telepathy. Once you have telepathy, you can communicate with the power source, and the power source can then do the magic tricks that you see in magic shows. Okay, well, let's move right on to the next listener phone call.
Yes, this is David. Station is 1270 WMKT, Central Lake, Michigan. I was just wondering, given the ignorance of the past, saying that one time we believed the earth was flat, blah, 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 what are the odds that we are so ignorant now that all of our physics and all of our understanding now is just completely wrong? And that there are so many things that we don't understand that it's just impossible for us to know really the fate of the universe and what's going on. Thank you.
Well, you ask a very embarrassing question, because that's a question that deep down inside every physicist has in the back of his or her mind. What if everything's wrong? What if this enormous artifice that we're building is actually built on a foundation of sand? Well, let's put it into perspective. You see, Einstein did not disprove Newton's theory. Newton himself did not disprove the theory of Galileo. Each of these theories work in a certain domain. And as long as you stay inside that domain, these laws work perfectly fine. For example, at low velocities, Newton's laws of motion work perfectly fine. If you want to send a space probe all the way to Saturn and fly it through the rings of Saturn, you use Newton's laws of motion. You don't have to have Einstein's laws because you're not near the speed of light, and gravitational fields are rather weak around Saturn. And so in the domain of the solar system and the domain of weak velocities, Newton's laws of motion work perfectly well. Now, once you reach the speed of light and you have very large objects like galaxies, then you have to use Einstein's theory. But then Einstein's theory will also break down. In fact, Einstein himself realized that. That's why he was trying to create a higher theory, even beyond his own theory, called the unified field theory. He failed. After 30 long years, he failed. But the point I'm raising is that every great theory builds on the past. Each theory works in a certain domain. And so will all physics collapse? No. At low velocities, Newton's laws of gravity work perfectly fine. At high velocities, we use Einstein's theory. But then at super high velocities, like in the center of a black hole, we may have to use string theory. Well, let's take a short commercial break.
This is Science Fantastic.
Okay, well, let's move right along to the next listener phone call.
Hi, why not a Dyson swarm utilizing mylar sheets? They could be blown away by the solar wind, but there could be some energy to keep it in place. I don't know, just asking.
All right, well, you ask a very interesting question. Well, one of my colleagues, a fellow physicist, is Freeman Dyson at the Institute for Advanced Study at Princeton, where Einstein worked. And he has come up with some rather novel and bizarre ideas. He claims that a Type 2 civilization, that is a civilization that can play with stars and has stellar energy, how would they power their machines? They would power their machines, he said, by encircling the sun with a gigantic sphere called the Dyson sphere that would then absorb 100% of the energy of the star. It would be super efficient, and they could use that to energize their machines. Now, some people pointed out, well, isn't that a lot of material? Why not have swarms? Swarms of, let's say, balloons or light-catching satellites that orbit around the sun, called a Dyson swarm. Why not use them to extract energy? And so, well, let's take a short commercial break. And after the break, we're going to talk about whether or not mylar or any other substance can be used to harness the energy output of an entire star. And some people think that maybe we've already seen one in the heavens, a sign of an alien civilization in outer space.
You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Hey, the lines are open. So, moving right along, previous phone call was about Dyson swarms. And so, once again, a very advanced civilization will harness the energy of the sun, either by encapsulating the entire star with a sphere or using a swarm of smaller satellites to capture starlight. And the question is mylar good enough? Well, the short answer is no. First of all, you need to have tremendous amount of this material that is super tough, that's not going to shred. And we think the solution to the problem could come from nanotechnology. There's something called graphene. Graphene is perhaps the strongest substance known to science, stronger than diamonds, in fact, and it's made out of pure carbon, just like diamonds. It turns out it consists of one sheet of carbon atoms arranged in a lattice. And we've actually can make small quantities of graphene in the laboratory. It is so strong that you can get an elephant, suspend the elephant on a pencil, and suspend the pencil on graphene, and graphene will not rip. You can actually sustain the weight of an elephant using graphene and using the elephant suspended on a pencil. That's how strong graphene is. Now, what's the catch? There's always a catch somewhere, right? Otherwise, we would have these things right now. The catch is you cannot create pure quantities of graphene except in small amounts. Something smaller than a postage stamp. That's the world's record of what we've been able to do with graphene. But one day, when we perfect the engineering of graphene, we'll be able to have all sorts of fantastic things. First of all, bridges. Bridges that are almost transparent. Bridges held up by threads of graphene, stronger than steel. So there you are riding in your car, and the bridge is practically invisible. Or a space elevator, an Eiffel Tower into outer space. That could be possible if you have graphene, because we know from Newton's laws of motion that steel is not strong enough to support a space elevator into outer space, but graphene is strong enough. And so once again, that is another potential application of graphene. And so once again, if we have graphene, we could have Dyson swarms, we could have space elevators, we could have bridges that are transparent. All sorts of things are possible. Then the next question is this all science fiction? Do they exist out there in outer space? Well, last year, headlines in the science world were made by the discovery of an object that eclipsed the mother star in outer space, an object that is perhaps hundreds of times larger than Jupiter. If Jupiter were to go in front of our sun, starlight from our sun would damp by about less than 1%. You got that? About 1%. However, in outer space, we saw evidence of a star whose starlight dipped by about 40%. Now, this freaked out the world of astronomy. This is not supposed to happen. We're not supposed to see a shadow of an object so large that it can dim starlight by about 20% or so. So what is it? Well, to be very frank, we don't know. The world of astronomy still is debating this question. We're simply waiting for the next occurrence of this shadow. Some people say, aha, it's a Dyson sphere in outer space. These are called megastructures. If you want to know more about them, Google the word megastructures, and you'll realize that there's quite a bit of controversy around what scientists have seen in outer space. Is it evidence of a Dyson sphere? Is it a smudge on somebody's telescope? Is it a swarm of comets? The short answer is we don't know. Well, maybe you can figure it out. Google the word and find out about Dyson spheres and Dyson swarms and megastructures in outer space. Okay, moving right along. Let's take the next listener phone call.
Hi, Dr. Kaku. I really enjoy your radio show, and I have a question. In the series Cosmos that Neil deGrasse Tyson redid, at one point he says that there are more atoms in what is ejected from a sneeze than there are stars in the universe. Is this true, or is the number of stars truly infinite, as we were taught as kids? Thank you.
Well, I think you have to add the word visible universe. Otherwise, well, we really don't know how big the universe is, quite frankly. But let's break it down. How many stars can you see in the Milky Way galaxy? Roughly 100 billion. You got that? Well, how many galaxies out there that you can see with the Hubble Space Telescope? That's the visible universe. And the answer to that is also 100 billion. So how many stars are there in the visible universe? Well, obviously, it's 100 billion times 100 billion. Is that smaller than the atoms of a sneeze? Yes. In fact, that is smaller than the atoms on the tip of a needle. You have trillions upon trillions of such atoms, dwarfing the number of atoms, of stars that you get in the visible universe.
This is Science Fantastic. Science Fantastic with Professor Michio Kaku.
This This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And once again, in this hour, you guessed it, we're going to throw the lines open because we want you to be part of the action. Okay, well, let's get right to the next listener phone call.
Yes, how do you, what math, geometry, what kind of math do you use to calculate structural analysis of a three-dimensional object in order to accomplish and determine how to balance pressure, pounds per square inch, of a three-dimensional structure, possibly a rectangle with a length, a width, and a depth, to know how to balance pressure from all all 6 sides of it. What type of math do you use? Do you use algebra, a type of mathematics, or algebra, or geometry, or trigonometry, calculus?
Well, when I was a kid, I used to ask that exact same question. I grew up in California, and I used to see pictures of skyscrapers in Manhattan. And I said to myself, now, wait a minute. You can't build a scale model of the Empire State Building that's that big and then go on to build it. They must have made a small-scale model, but then how do they know it's accurate? I mean, what mathematics is required to build the Empire State? How do you calculate the tension on a brick at the bottom of the Empire State Building? Well, I'm a physicist now, and I actually teach Newtonian mechanics to freshman students here at the college, and that's exactly what we do. We can calculate the tension on every single block of the Empire State Building in 3 dimensions. And what is the mathematics that we use? It's called vector calculus. Now, what is a vector? A vector is basically an arrow with a certain length associated with it. And each arrow represents a force. And so if I have a brick at the bottom of the Empire State Building, I calculate all the vectors that are impinging upon the brick from all the bricks that are on top of it. Vectors can add. And when I add up all the vectors from different directions, then I can calculate what is the tension on a brick at the bottom of the Empire State Building. And these vectors work in 3 dimensions. Arrows can point in any of the 3 directions. Therefore, to define an arrow, you have to have the x component, the y component, and the z component, and the length. So each arrow has 4 numbers associated with it. The length, that is the strength of the force, and 3 directions, which tell you which way the vector is pointing. And then the last statement given to us by Isaac Newton is that no matter what brick you're looking at in the Empire State Building, the sum of all the arrows must be 0. And that's the key. When you want to then calculate how much tension there is on every brick in the Empire State Building, you take all these arrows from all the previous bricks, add them all together, and bingo, you now know the force acting on every little piece of the Empire State Building. That's why we don't have to build a scale model the size of a building in order to calculate the strength of the force of gravity and the tension on every brick. Now, these vectors can also work in 4 dimensions, 5 dimensions, 6 dimensions. In fact, they can work in hyperspace. And when these vectors start to describe protons and neutrons, then you start to have something called tensor calculus, that is the calculus of Albert Einstein, and then you start to work in general relativity and gravity and even string theory. And so starting with these little arrows with certain lengths and a direction, you can build up a tensor calculus, which is then the language that we physicists use when we discuss black holes, the Big Bang, and hyperspace. Okay, well, moving right along now, let's take the next listener phone call.
Hi, I'm Weston. I'm from Chattanooga, Tennessee. I was wondering what your opinion was on the hollow earth theory. Thanks. Bye.
Well, believe it or not, I actually get quite a few questions about the hollow Earth theory. First of all, how do we know what's inside the planet Earth? No one's been there. You can't drill a hole there. But actually, we know quite a bit about the center of the Earth. First of all, we can have gravitometers that very accurately measure the gravitational strength on every point of the Earth. For example, that's how we discovered the gigantic crater in the Yucatan of Mexico, the remnants of a meteor or asteroid which plowed into the Yucatan, destroying the dinosaurs. That crater is about 180 miles in diameter, and it was found not by looking at it from outer space, not by using cameras, not by excavating the area. No, it was found by oil exploration engineers of Pemex who were looking at gravitational anomalies. As they moved their gravitometer across the Yucatan, they found that there was a circular crater which created a circular disturbance in the gravitational field. That's how accurate gravitometers are, that you can pick up all sorts of stuff from the inside of the planet Earth. And that's, first of all, how we know that the Earth is solid and does not have a hollow core. Next, we also have Newton's laws of gravity as they apply to the Earth going around the sun. From that, believe it or not, we can calculate the mass of the planets and the mass of the sun. We know the radius of the Earth. We know the density of rock. And bingo, we can now compare the calculated density of the Earth with the actual density of the solid Earth. And bingo, once again, you get a solid Earth. And so for many reasons, stemming from our understanding of rock and our understanding of Newton's laws of motion and gravity, you can show that the Earth is indeed solid. All that without having to drill completely through the center of the Earth, using the power of mathematics. Now, you may say to yourself, well, why should we believe the laws of Newton? These laws are used in every single space probe. They are so accurate that we could put a space probe right through the rings of Saturn launched from the planet Earth. That's how accurate Newton's laws are. And we use Newton's laws to show that the Earth is indeed solid and not hollow. Okay, well, moving right along, let's take the next listener phone call.
Yes, Dr. Kaku. My name is Mike. I listen to you on KONA in Pasco, Washington. And my question is simply this. What was going on 1 second before the Big Bang? Was there anything? Something happened. What was going on? Thank you so very much.
Well, they sometimes say that physicists are the only scientists to whom you can say the word God and they will not blush. However, if you want to see a physicist blush, you have to ask them a simple question. What happened before the Big Bang? At that point, we physicists start to babble incoherently because the framework by which we analyze the Big Bang comes from Einstein's theory of gravity, and Einstein's theory breaks down at the center of the Big Bang, and so they are useless. So Einstein's theory says nothing about why it banged, what banged, or anything about the nature of the bang itself. Einstein's theory simply said that there was a bang, and we can now calculate the properties of what happened after the bang. We need a higher theory, and again, the higher theory is string theory, which has not yet been proven. That's why we string theorists don't get Nobel Prizes, because it has not yet been proven. That's the acid test. When you want to prove something, you have to have an experiment that proves it to be correct. However, we do have the theory, and the theory does give us an inkling as to what happened before the instant of the Big Bang. First of all, Einstein's theory gives us a picture of the universe being a bubble of some sort. Every scientist has this balloon that we use in astronomy class, and we inflate the balloon, and that describes the expanding universe. We are like bugs that walk on the surface of the balloon, but the balloon is expanding. And then we also believe, using string theory now, that there are other balloons out there In fact, if each bubble represents a universe, then we have a bubble bath of universes. And so the new paradigm coming out of string theory is the multiverse of universes. Now, when these universes collide, that's when you get the Big Bang. Or when universes bud into two universes, you can also get a Big Bang. So what happened before the creation of the universe? The collision or the fissioning of universes.
This is Science Fantastic.
Okay, well, let's go right to the next listener phone call.
My name is Walter. I'm at station 103.1 WILK in Scranton, Pennsylvania. My question is, considering how a penny drop from a high altitude can crack a sidewalk, can a string, if in a suitable atmosphere, have enough mass to do likewise and perhaps even slice through an object? Or what would the object's mass have to be in order for that to occur? Thank you.
Well, I live in New York City, and every tourist that comes to New York City wants to visit the Empire State Building. And what do they want to know? They want to know if you throw a penny off the Empire State Building, is it going to create a crater on Fifth Avenue when it hits the ground? Well, all the tourists, after visiting the Empire State Building, they look outside and they look for evidence of a crater, and they see none whatsoever. But you may say to yourself, now, wait a minute. When objects fall, they accelerate according to Newton's laws of gravity, and there should be all sorts of craters on Fifth Avenue. Nope, that's not how it works. What happens? And the answer is friction. Because of friction, the penny reaches terminal velocity. There's a point at which it doesn't get any faster at all. When it reaches terminal velocity, which is just a few hundred miles an hour, it then bounces off the ground because it's not reaching thousands of miles per hour. Same thing with strings. Because of friction, strings will float. They're not going to even reach terminal velocity at all. They're going to float on their way down because they have so much air friction. Now, we can put air friction into Newton's laws of gravity, and when we do that, yes, we find terminal velocity. And this is also the reason why one person actually fell out of an airplane and survived. This is an incredible story. I was rather amazed when I saw this story. There's one documented case where a plane broke up in mid-flight. A stewardess was caught near the bathroom, and when she fell, she was protected by the steel of the bathroom, the back of the plane, and she survived. How did she survive? Because she reached terminal velocity. That is, the endpoint velocity. You cannot get faster than terminal velocity as you go through air because of air friction. And that's why Fifth Avenue is not pockmarked. Okay, moving right along, let's take the next listener phone call.
Hi, my name is Leon Wansick from Nanticoke, Pennsylvania, and my question is, if the Earth lasts long enough, will all the mountains in the world eventually be back underneath water and oceans again someday in the future? Thank you.
Well, you ask a very interesting question because if you go back in our own history, going back hundreds of millions to billions of years ago, you realize that the geometry of Earth was quite different. And if you travel in the Midwest, you're rather shocked to find seashells in the middle of nowhere. How did that happen? Well, we'll answer that question after the break.
This is Science Fantastic. You're listening to Science Fantastic with Professor Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Okay, well, before the break, we had a question, and that is, what will the Earth look like millions of years from now? Will we be underwater? Well, it's possible. First of all, if you go travel in the Midwest, sometimes you realize that looking in the plains, you see seashells. And you say to yourself, well, that's impossible. I mean, how can there be seashells in the middle of the Midwest? And then you come to the rather astounding conclusion that where you're traveling used to be the bottom of an ocean. And that's one reason why you'll see seashells in the middle of nowhere, thousands of miles from where the oceans were. And if you go back just 10,000 years to the last glaciation, you can see that the shape of the continents change. When you start to go hundreds of millions of years into the future, then the continents themselves have rearranged themselves many times. And this process is going to continue because the center of the Earth is churning. And why is the center of the Earth churning? Because it's radioactive. Believe it or not, the reason why we have volcanoes, the reason why we have earthquakes is because the center of the Earth is radioactive. It is hot as a consequence of that. Hot because of the decay of thorium and uranium and other radioactive materials. And that causes a churning of the material at the center of the Earth. And when this churning material reaches the surface of the Earth, it causes the continents to move. The continents are moving because they're pushed by the movement of hot magma, which in turn is pushed by the flow of radioactive materials and heat upwards toward the surface of the Earth, originating from the center of the Earth. And so you realize that, yes, hundreds of millions of years from now, believe it or not, where you are sitting right now could be at the bottom of an ocean. Okay, well, without further ado, let's just jump right into the next listener phone call.
Hello, I have a question about the speed of light, and if you have a flashlight, doesn't that mean that those light particles are moving at about 3 times 10 to the 8th meters per second, which is not capable, nothing is going faster than that on the Earth?
If you have a flashlight, is it true that the photons of the flashlight travel right at the speed of light as soon as they leave the flashlight? And the answer is yes. Light consists of photons. We've clocked these photons. We've clocked them traveling at the speed of light. And as a consequence, we do believe that all light travels at the speed of light. Now, one thing that I did as a child was I took a flashlight and I whizzed it across the night sky. And then I said to myself, wait a minute. The flashlight just whizzed across the night sky, or across hundreds and hundreds of light years. Therefore, did the light beam go faster than the speed of light? And I thought to myself, well, maybe it did. Maybe it broke the light barrier just by flashing a flashlight, because I went from the south direction to the north direction by whizzing the flashlight across, and bingo, I must have broken the light barrier. Wrong. I now know how the whole thing works. It turns out that the image that you create by flashing a light beam across the night sky can in fact change faster than the speed of light. But each individual photon does not. For example, let's take a hose, a fire hose, and I move the fire hose across the sky. At first you say to yourself, wow, the fire hose just went right across the night sky, much, much faster than the velocity of ordinary water. And then you realize, no, each droplet of water went as fast as water goes inside a fire hydrant. But the image of the water flashing across the night sky, yes, that went really fast, much faster than the speed of water coming from a fire hydrant. Now, images can go faster than light, but material objects cannot. And that's the answer to the puzzle. Can you go faster than the speed of light by flashing a light from east to south and west? And the answer is no. Material objects, including light, cannot go faster than light. But the image the image created by these objects can in fact go faster than the speed of light because these images aren't made out of anything material at all.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again on Science Fantastic, we profile some of the most amazing developments in science, and you can be part of the fun by calling 866-323-2129. Okay, well, moving right along, let's move on to the next listener phone call.
Thank you for taking my call, Professor. This is Mickey from East Point, Michigan, and I listen to CKLW Channel 800 AM. Last week, you mentioned the moon might be a part of the Earth, and I was wondering if that were true, what part of the Earth would it have come from? Maybe from somewhere under the ocean, or maybe the Grand Canyon. Thank you.
Well, you ask an interesting question that professional astronomers have asked themselves, and that is about 4.1 billion years ago. It's conceivable that the evidence points to the fact that the moon was blown out of the Earth. There was an object about the size of Mars that collided with the Earth, blew out a tremendous amount of debris into outer space, and gravity began to compress the debris, and it formed the moon. Now, what did the Earth look like back then? Well, the Earth probably looked a little bit like Pac-Man. That is, a gigantic chunk of the Earth was gouged out, and remnants of that should be visible today. And some people have asked the question, well, what about a gigantic super crater that might exist on the surface of the Earth? Well, as I said before, gravity compresses the material of the early Earth, compresses it back into a circle, into a sphere, and that's why objects are round. Some people ask, well, why is the sun round? Why are the planets round? Why is everything round out there in outer space? Well, except for smaller asteroids, yeah, everything is round in outer space because of gravity. As we say in astronomy class, gravity sucks. Gravity sucks evenly, and that's why we have the stars, and that's why we have the sun round shape. Now, some people think that maybe the Pacific Ocean is a remnant of the object that was hurled out of the planet Earth. But hey, that was 4 billion years ago. And so we simply don't know where the moon came out of. Your guess is as good as mine. Are open. Okay, well, moving right along, let's take the next listener phone call.
Hi, yes. When you have time, can you please explain to us or me what is the force of gravity and why do we have it? Thank you.
Well, you ask a question that bedeviled scientists going even before the work of Galileo. Newton did not know the answer to that question. He simply invented something called a force of gravity. What he did was he quantified the force of gravity and gave it equations by which we can calculate with it. But in his masterpiece, Principia, he states clearly, quote, hypotheses non fingo, meaning I'm clueless. I don't know. I frame no hypothesis about the origin of gravity. Now, Newton said that gravity attracts, but a lot of people criticize that by saying, now, wait a minute. Objects move because they're pushed by something. Something touches it and pushes it, but Newton invented a mysterious force which pulled on objects called gravitational pull. Well, Newton said flatly, I'm not going to frame any hypothesis. I don't know the answer as to what is pushing an object, making it fall. Well, along comes Einstein. He says, I got it. I now know what's pushing objects because every object moves because it's pushed. What is pushing the object is space itself. Now, think of a crumpled sheet of paper and think of ants walking along a crumpled sheet of paper. The ants would say, I'm being tugged to the left, I'm being tugged to the right. Something is pushing me, forcing me to walk in a crooked line. Now, we say to the ant, well, that's stupid. I mean, come on, give me a break. Your surface is crumpled. You're walking on a crumpled sheet of paper. There's no force at all. So Einstein said in the same way, that's the force of gravity. That gravity is caused by the crumpling of space. In this situation, the stretching and the squeezing of space is what causes gravity. So that theory works. We've tested it. We've tested it numerous times. We know that Newton's laws of motion are in fact wrong at high velocities. And now with the discovery of gravity waves just a few months ago, we have mathematical proof that the theory is right in every way that we've tested it. However, we should also point out that even even Einstein's laws of gravity eventually have to be replaced when we start to ask what happened before the Big Bang. But everything after the Big Bang can reasonably be explained by using Einstein's law of curved space-time. So why are you sitting in your chair now? Well, you may say to yourself, I'm sitting in my chair because gravity pulls me to the floor. End of story, right? Nope. Einstein says there's no such thing as gravitational pull. There's only the push of space over your head. So the reason why you're sitting in your chair is because the space above your head has been warped and is pushing you down into your chair. So objects do not pull, space pushes. That is Einstein's theory in one sentence. Okay, well, let's move right along to the next listener phone call.
Hi, this is Mac Milner calling. I live in the Tampa, Florida area. And my question is, do you think there is any validity to the theories or the news reports that you can find on the web about anti-gravity propulsion systems for flying saucers? The story goes that the United States recovered a flying saucer in Roswell, New Mexico, and reverse engineered it. And now the United States has several flying models, actually operational models of an anti-gravity energy sourced flying saucer, and they have about 9 of them is what the story says, and maybe more. Maybe you've read about that. Could you comment on it and tell us what you think?
Well, that would take several radios worth of time. We don't have that. However, let me just say a few brief remarks. You're probably referring to the Roswell incident of 1947. Now, the United States Air Force came out with a rebuttal, take it or leave it. Some people say that perhaps it's more disinformation from the United States Air Force. But the United States Air Force did come out with a rather thick volume trying to explain all the details of that incident. They say it was a weather balloon part of Project Mogul. And the reason why they classified it was not because there were aliens there, but because it was part of a secret experiment to calculate how radioactive materials disperse in the atmosphere in case of World War III. The Pentagon was preparing for World War. Not that it's going to happen, but it might happen. And it had to know the spread of radioactive materials as a consequence of that. Well, it's a long story. We've had pros and cons on Science Fantastic about flying saucers. I personally believe that, yes, the military has been withholding lots of evidence about these unexplained objects. Whether or not they're extraterrestrial, well, we'll discuss that on another edition of Science Fantastic.
This is Science Fantastic. Now, Science Science Fantastic with Professor Michio Kaku.
Scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, well, without further ado, let's take the first listener phone call.
Hi, Mr. Kaku. I'm Braden Holst. I'm 16 years old, and I was just wondering, what exactly are your thoughts about the universe at large? Thank you.
Well, you asked quite an ambitious question for a 16-year-old kid. The future of the universe at large. Well, let me try to break it down. We physicists believe that the universe was born about 13.8 billion years ago. It's a rather young universe, as universes go. It has many, perhaps trillions of years to go into the future. But as far as we can tell, the universe is not only expanding, but it is accelerating. And that shocked the hell out of many astronomers and cosmologists. We once thought that, the universe had an explosion. It was an explosive beginning, but it's slowing down and it's getting old. Boy, we were wrong. The Nobel Prize in Physics was given to 3 astronomers who made the discovery that the universe is not slowing down at all. It's speeding up, and we are clueless to understand why. In fact, if you can figure out why the universe is accelerating, you will win the Nobel Prize in Physics. And this has enormous cosmological consequences. If this acceleration keeps on continuing, then the universe will die. The universe will die in a big freeze. That is, things will get very cold. The universe will expand so rapidly that we won't even be able to see the stars. The stars will be so far away that the universe will be black. And astronomers living in this dark era will think that the Earth is the only object in the entire universe because there are no stars, and the stars have long since died out. Now, of course, this is still speculation because we don't know what drives it. We think it's something called dark energy, predicted by Einstein himself in 1916. It is the energy of nothing. In fact, it was Nikola Tesla who wrote eloquently about the whole question of, can a vacuum have energy? And the answer is yes. However, it's much smaller than Nikola Tesla conjectured. But on a galactic scale between galaxies, it adds up. It adds up so that there is enough dark energy, the energy of nothing, to make the universe expand and even accelerate. So that's one of the big unanswered questions in all of cosmology. Will we head for a big freeze? We used to think that the universe will head for maybe a big crunch. It'll expand, stop, and then start to contract, and eventually implode, and then perhaps a big bang happens all over again. That's called the oscillating universe. But at the present moment, we do believe the universe is not only expanding, but it is out of control, and we don't know why. And again, if you want a Nobel Prize in Physics, figure it out. Okay, well, moving right along, let's take the next listener phone call.
Hello, this is Patrick John, and I was wondering if you think light as well as the same constant in the universe will ever do more for fundamental physics than it already is. Thank you. Bye.
Okay, well, you ask a question that we physicists really do not have an answer to. Einstein, of course, said that the speed of light is central to his entire theory, and he said light is a constant, no matter how you look at it. So if a light beam is moving toward you, a light beam is moving away from you, or at right angles, or is on a rocket ship, the speed of light is a constant, no matter where you look at the thing. Now, then the question is, why is that? That's such a strange universe, because in order to make the speed of light constant in all frames, it means you have to have time itself distorted. Time itself slows down, speeds up, in order so that the speed of light is a constant. In outer space, the speed of light changes. The time changes to keep the speed of light constant. So our satellites, our GPS satellites, have to compensate for that, or else your cell phone cannot locate your position. Also on the moon, Time beats faster on the moon than it does on the Earth. Time beats slower on Jupiter than it does on the planet Earth. And the question is, why? Well, we don't really know. When we physicists try to concoct bizarre new universes, to start from scratch, well, usually we start with Einstein's theory. Step one is we postulate Einstein's theory. Now we have something called string theory, which postulates other universes. So for the first time, we have the possibility of other kinds of universes. So we think that, yes, there was a Big Bang, but Big Bangs can happen all the time because the Big Bang was a quantum event, meaning that there's uncertainty, meaning that it could happen again. And if it happens again, perhaps in these other universes, the speed of light is different. Well, all of this is conjecture. We have the theory, string theory. It does predict that there could be other universes out there with different laws of physics. Unfortunately, our Large Hadron Collider, the largest machine of science outside Geneva, Switzerland, is not powerful enough to conclusively prove or disprove string theory. So we're going to have to wait for other experiments. And in my book, Parallel Worlds, I give you a series of other experiments which may one day give us a confirmation of string theory. And in string theory, yes, there are other laws of physics in other universes.
This is Science Fantastic. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Science Fantastic is open mic on Science Fantastic. Okay, well, let's move right along to the next listener phone call.
Yes, this is Charlie the plumber from sunny downtown Augusta, Florida, where the sun is always shining. And today we're getting liquid sunshine that's everywhere. Now, my question for the good professor is, if you're traveling faster than the speed of light, how can you outrun your headlights? I mean, I believe that if you're traveling faster than the speed of light, your headlights aren't going to work, you know? So I know Einstein's theory may be a little bit different, but how can we prove this theory? Charlie, Augusta, Florida. Thank you.
Well, you ask an interesting question that has puzzled a lot of people, school kids, parents, just the average person wonders, if you're in a rocket ship traveling at the speed of light and you turn on a flashlight, doesn't the light beam go faster than the speed of light? Because after all, you're on a rocket ship that's traveling right near the speed of light. So how does that work? Well, look, we measure this. Every day we measure it. In fact, with laser beams now, we can even do it on a tabletop. Believe it or not. Yes, on a tabletop, we have fiber optic cables right on the physics laboratory. We shoot a laser beam right in that fiber, and we can actually calculate and measure the speed of light. And your cell phone takes this into account every day because time beats a little bit slower as satellites go faster and faster. Our astronauts are a few microseconds, perhaps, younger than normal, than a twin sitting on the Earth because of this effect. And so, in other words, we've measured this thing. We've even taken airplanes and put atomic clocks into an airplane and radioed the information back down to Earth. And again, your GPS satellite does it all the time. Each time, Einstein's theory comes out right. So you cannot go faster than the speed of light because as you approach the speed of light, your clock goes slower and slower, and you get heavier and heavier, and you get flatter and flatter. Now, all that may seem to violate common sense, but all I can say is that Mother Nature couldn't care less about your common sense. That's just the way it is. And a simple consequence of this, it only takes about 1 page of mathematics to demonstrate this. We do this for our physics students, in fact. It only takes 1 second to demonstrate that if time and space change, then so does matter. And as matter accelerates, it turns into energy exactly by E equals mc squared. In fact, that's where E equals mc squared comes from, because the faster you move, energy turns into mass, precisely by the equation E equals mc squared. In fact, that's how we derive it for our physics students. And again, isn't that a crazy universe? Well, all I can say is, hey, that's just the way it is. Sorry about that. Okay, well, moving right along, let's take the next listener phone call.
Yeah, my name is Roy from Mulberry, Florida. If everything has a beginning and has an end, then how is there space? Space goes on forever, and it always has been, or in theory it always has been, because what else would there have been before it? Even without the Big Bang, there still should have been space. So I don't understand. So maybe you could explain it. Thank you.
Well, to be quite frank, we physicists don't quite understand it either. First of all, this question goes all the way back several hundred years into the past. Even Isaac Newton pondered this question. And the question is rather simple. If the universe is infinite and the universe is uniform, these are two postulates that most common sense scientists come up with. The universe is infinitely old and the universe is uniform. Almost immediately you have a contradiction. A contradiction. It is impossible. Because if there are an infinite number of stars and the density of the stars is uniform, then the night sky should be white. And your eyes should melt because of all the radiation coming down on you. But the night sky is black rather than white. And so this is one of the great paradoxes of ancient science. Why is the night sky black but not white? If there's an infinite number of stars, it means that everywhere you look, sooner or later, a light beam will hit your eyeball. That means an infinite amount of light will hit you from an infinite number of directions. In other words, your eyes should melt. So the fact that the universe seems to be uniform, seems to be infinite, is a contradiction. And after the break, we'll talk about how modern scientists resolve this whole question. After the break, we're going to try to take a stab at the question, is there an end to space? Is there a brick wall out there that says, the end? This is the end of the universe. Do not pass go. Will our rocket ship one day crash into this barrier? Well, find out after the break.
You're listening to Science Fantastic. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in physics and science. And we had a question that came in. And the question is, well, is the universe infinite or finite? Did the universe have a beginning or does it have an end? Well, we do think, as far as time is concerned, that the universe did have a beginning. The beginning, we think, was 13.8 billion years ago when we had this cataclysmic explosion that sent the galaxies hurtling out in all directions. And so that's called the Big Bang Theory. And then the other question is, what about space? Does space go on forever, or is there a brick wall out there that says the end? And if there's a brick wall out there that says the end, what's on the other side of the brick wall? Well, our best idea is that the universe is a bubble of some sort, like a balloon. We live on the skin of the bubble, like ants walking on the surface of a balloon. And, of course, the surface of the balloon has no end. You can go all the way around the bubble, the balloon, and never hit the end. And here's an example of how in 2 dimensions, that is the world of an ant, in 2 dimensions, the universe seems to be infinite. The ant can go in any direction and never, ever reach the end. But in 3 dimensions, it's just a balloon. It's finite. So one possibility is that the universe is infinite in 3 dimensions, so that if you walk in any direction, you're never going to hit a brick wall. But if you had 4-dimensional eyes that we don't have, then you would see that the universe is actually a soap bubble, that you're simply going around the universe over and over and over again. Now, that is a theory. Another theory is that perhaps the universe really is infinite in all directions. But what does physics say about this? And the answer is it's inconclusive. Okay? We do think that there was something called inflation, inflation, which was a gigantic amendment to the Big Bang Theory, and that is the universe accelerated much faster than we previously thought. That's called the inflationary theory. But the inflationary theory has a footnote, and that is inflation can happen again and again and again. It's a quantum theory, meaning that there are perhaps other universes out there. So think of a bubble where baby bubbles peel off and create other bubbles, and you get a bubble bath of a multiverse of different universes. And so the question is the universe infinite or finite becomes even worse. Now we have perhaps an infinite number of universes, and each universe may be finite or infinite. And that's the state of where we are today. So sorry about that. I wish I could give you a definitive answer to the question, is there a wall out there? Well, perhaps not. Perhaps the universe can be finite or infinite even without a wall, because it could be infinite in 4 dimensions, infinite in 3 dimensions, but finite in 4 dimensions. And so we're still waiting for our latest evidence from what is called the Planck satellite. We have a satellite there launched by the Europeans, the Planck satellite, and hopefully we'll get enough data to begin the answer first question, and that is inflation correct? If inflationary theory is correct, this means there could be parallel universes, with universes budding off our universe all the time. And then, of course, everyone wants to know, is Elvis Presley still alive in one of these parallel universes? Well, it can't be ruled out. Yes, perhaps the king is alive in a parallel universe. Okay, well, let's move right on to the next listener phone call.
Hi, this is Brian from Anchorage, Alaska. I listen to your show on KFQV. My question is, compared to the amount of silver that's been mined, how much is still left in the earth? Thanks.
Well, that's an interesting question that you could actually apply to gold, oil, almost any number of different kinds of minerals. And that question was actually asked about oil, for example, by a petroleum engineer back in the 1960s by the name of Hubbard. Hubbard postulated something called Hubbard's peak. And that is, when you take a look at silver, gold, or oil, you have to look at the point at which 50% of that material has been taken out of the earth. Because once you reach the 50% point, it means that every year you're going to get less and less of this material coming out of the earth, and prices could skyrocket as a consequence. Well, when Hubbard made that statement about oil, which also applies to silver, he was ridiculed because at that point, Texas was still gushing with all sorts of oil. We had oil that we didn't know what to do with, and it seemed as if the gusher of oil would last forever. And here was Hubbard saying no, that there is a point at which we'll hit the 50% point. Well, after Hubbard made that prediction in the 70s, we hit Hubbard's peak. Yes, we actually hit Hubbard's peak. And America became a net importer of oil, which shocked the hell out of the establishment, which once thought that we could just take as much oil as we want out of the surface of the earth. Well, let's take a short commercial break, and I'll try to answer a question. Are we hitting Hubbard's peak now for world consumption of oil, and what about silver and gold?
This is Science Fantastic. Listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. It's open mic on Science Fantastic. Well, before the break, we had a question about, are we going to run out of silver? And the short answer is no, because we will always have silver and gold and other chemicals somewhere else in the universe. But the relevant economic question is, have we hit the 50% point? When it comes to oil, many analysts thought that world consumption of oil would hit the 50% point probably sometime in this decade. However, Hubbard was very careful to say that the 50% point also depends on technology. If new kinds of technology come in that find new kinds of oil reserves. Now we have fracking. And as a consequence, we know that, yes, a new source of cheap oil has, in fact, been discovered via fracking. And that's the reason why the price of oil has plunged in the last year. That's why the governments of Venezuela, Iran, and Russia are being rocked because of the fact that because of fracking, it means that the price of oil has just plummeted around the world. So what about the other chemicals? Each chemical is different. We have not yet, we think, hit the Hubbard's peak for silver, but how much silver is there in the entire world? And that we don't know. We begin to understand Hubbard's peak as we hit the top point and we begin to deplete our supplies. But right now we have not yet hit Hubbard's peak with regards to silver. So the short answer is, well, we don't really know for sure. Okay, well, moving right along, let's take the next listener phone call.
Hello, Dr. Michio Kaku. My name is Ben McConnell. I'm calling from KSPT, Sandpoint, Idaho. Do weightless dynamos spin free in a vacuum, like the Earth? Could spinning dynamos in Earth orbit beam energy down into the grids? Sunlight can add energy to the spinning generators. What kind of beam would work best? Could this be our primary power source? Thank you.
Well, the short answer is that yes, you can have spinning dynamos in outer space that would then generate electricity. However, it's not economical. We have something called the conservation of matter energy. So, in other words, if you extract energy out of a dynamo, the dynamo begins to slow down. You have to have another energy source, like maybe the sun, to drive the dynamo. So in the short term, the answer is no, you cannot get net energy unless energy comes in from the outside, like, for example, maybe the sun. Well, let's take a short commercial break.
This is Science Fantastic.
It's fantastic. We profile some of the most amazing developments in science and technology that affect your life and your understanding of the great universe that we live in. Okay, well, moving right along, let's take the next listener phone call.
My name is Dudley Flott. I live in Foley, Alabama. I listen over the internet with WEBY 1330 AM. And the question I have, I understand pretty much about the black holes. What I would like to know is if any ellipses occurred from a star passing between the Earth and the black hole. Thank you.
Well, the short answer is no, but eventually it will happen. And so let me explain the dynamics of what you're talking about. First of all, there are two kinds of black holes that we see in outer space. One are the galactic black holes lurking in the center of galaxies, and they are huge, humongous. They weigh millions of times more than the mass of our sun. And then you have the stellar black holes, like our sun. They're just several times more massive than our sun, and they are much smaller as a consequence. So when we look at outer space, we do look for stars where planets can eclipse them, and these are called transits. So if we have a planetary system in outer space and a planet moves in front of the mother star, then starlight dims slightly. It dips slightly. We measure that with the Kepler satellite, and that's how we know the presence of that planet, by looking at these mini eclipses of the mother star. Now, black holes are different. Black holes are black. As a consequence, you cannot get much light radiation from them, and you certainly cannot see a dip in the light that comes out of them. So an eclipse from a black hole, well, it'd be nice if we could do it, but it doesn't seem likely because the black hole itself is dark. However, we do see something else, and that is we see Einstein rings. Einstein said that space itself is like glass. When light goes through glass, it bends. That's how you know that you're wearing your glasses, because even though glass is invisible, light bends, glass bends light. And as a consequence, you know you're looking at glass. Well, the same thing happens to space. If there's a galaxy in front of you, light will go around the galaxy and bend. And as a consequence, it looks as if a galaxy is actually a magnifying lens of some sort. This means you have optical illusions, and they're called Einstein rings. So when you look at a galaxy, you can actually see rings and carbon copies. This is amazing. When you go to a house of mirrors, you see copies of yourself in the house of mirrors, because light does not move in a straight line inside a house of mirrors. And if you look at a crystal ball, same thing. You can see copies of yourself in a crystal ball. Well, it turns out that galaxies will also act like a crystal ball, will also bend light, giving you false images. And we see them in outer space now. They're called Einstein rings. Go to the web and you can type in Einstein rings, and you can actually see these things. And can a black hole create an Einstein ring? Yes. So even though we don't think that eclipses of black holes can be seen anytime soon, the Einstein rings created by black holes, we think, can be seen. Okay, well, moving right along now, let's take the next listener phone call.
Hi. My question is, if you dug a hole all the way through the Earth, from one end to the other, going through the core, and you jumped in that hole, would you stop in the middle of the Earth, or would you keep on going? Thank you for taking my call.
You ask an interesting question that actually I was given when I was a freshman at Harvard learning physics for the first time. Believe it or not, if you drill a hole right through the center of the Earth at any angle, it doesn't have to go right through the center of the Earth, but at any angle, a straight line right through the Earth at any angle, and you drop a ball, the amount of time it takes to go across through the Earth is the same even if the tunnel is a few hundred miles long versus a tunnel which is 8,000 miles long. And to answer your question, no, you do not fall and stop. You go right through the center of the Earth and keep on going, such that when you finally arrive in China or someplace on the other side of the Earth, you will be at rest, because it is symmetrical. It is symmetrical in terms of the fact that you accelerate as you go toward the center of the Earth, and you decelerate as you go toward the other end of the Earth. And the total transit time, you can do the calculation yourself. It was given to me when I was a freshman. The total transit time, I forgot. It's on the order of a few hours. But yes, you can actually calculate that time, and it is the same even if the angle of the tunnel is different. As long as the tunnel is in a straight line right to the center of the Earth, you can calculate the amount of time it takes. If you were to drop yourself into this tunnel, you can calculate that number. So you do not stop. If you go through the center of the Earth, you go right through to the other side. Okay, well, unfortunately, that's it for Science Fantastic. Good day.
You're listening to Science Fantastic with Professor Michio Kaku.